All right. So I just got through mentioning enthalpy a second ago.
Switch them in the wrong class. But that's all right.
What class are you supposed to be in?
Into that carpentry with
Yeah, CCSN 283.
Yeah.
Yeah, you're here.
Okay, this is
you made it. Yeah, nice work.
Okay. When I saw the circuitry, I thought, oh, this is cool. I didn't get into this.
Now, like today's lecture is just physics and heat transfer.
Oh.
So we started out with energy and power.
No problem.
Right on, right on.
Yeah.
So let's look a little bit more into heat. Early in the lecture, I mentioned that a house is pulling in about a kilowatt, and that's just electricity. In general, most houses, and you'll see this in your Dorsey and Krieger, most houses consume about 5 times the amount of thermal energy that they do electrical, right? So if we just take that, that 1 kilowatt, and let's just say you actually don't have wood or gas heating, and you're doing it all in electrical, you can basically say, okay, now my house is running at 6 kilowatts because my heating is 5 times my electric, et cetera, et cetera. Let's do a little calculation and see how much thermal energy is inside a house. Let's do that, and then we can actually take that and convert it into dollars, because at the end of the day, that's what this is all about. I think, maybe.
It's going to BTUs to kilowatt.
Yeah. All right.
Volts to kilowatt.
And this is also a good segue. We're talking about energy densities. You know, hydrogen as a fuel, for example, is not as competitive as it might be with other conventional fuels because its energy density is low. So let's look at the relationship between mass and volume in the case of a house, and just see how much thermal energy is inside a house and how much it's worth. When we get into the blower door, this will make a lot more sense too. Okay, so what's a reasonable sized house? Kind of an average, decent.
1,500 square feet.
Yeah, 1,500, 2,000. You know, if you're in the park, maybe a couple of cardboard boxes. So what we'll do, and we'll play around a little bit with units conversion here too, is I think we typically think in conventional units, but then we'll convert it. We'll do a little units conversion too. Okay, so the house is 2,000 feet squared. How tall is the ceiling? Well, 8 feet, right? Let's just say. Yeah, we're just yeah, back of the envelope. So what's the relationship between height, volume, and area? Let's do a little math here. So this is V for volume. What am I going to multiply by what?
2,000 by 8.
Yeah, so 2,000 is my area. H is my height, that's 8 feet. So I'm just going to, again, 2,000 feet squared. Multiply that by 8 feet. Now, there are there's only 2 parts of this problem. I've got the number and I've got the units. I don't have any kilo whatever. So I could say that's 2 kilo square feet, but forget that. We don't need to mess with that for now. So equals. There we got 16 followed by 3 zeros. 16,000 cubic feet. Did I do that right? How big is your house? I got a 16,000 cubic feet. So list your house in list your house in cubic feet instead of square feet. Like, oh, is that big, small? A lot of times I'll just bop out here to Google, and let's just do cubic feet to cubic.
Each figure your elevation and your
Beg your pardon?
Wherever the house is built, the elevation has a big part of heat.
Because what?
Because of the height, the elevation, like if you're at sea level, you have 14.5, but every 1,000 feet you add another 3%.
Oh, for density?
Yeah.
Oh, yeah, we're not gonna worry about density for now. That's gonna be that'll be like maybe a 2 to 5% error, but it won't affect the overall answer. Yeah, but thanks for mentioning that. Okay, so 1 cubic foot is 0.028. We'll just go with 3 significant digits, 0.028. So we'll pull up the calculator. What did I say? 16,000 times, we'll use 3 significant digits, 0.0283 equals. So the house is 452 cubic meters. Let's just call it 450. Keep it simple. 450 meters cubed. Okay. Eventually in this class, you'll probably cover what are called heating degree days. And basically all that is, let's just say it's actually kind of warm outside. Let's just say it's 40 degrees outside. We want it to be 60 degrees in here. That's a 20-degree difference. If we wanted to maintain that difference all day long, that would be 20 heating degree days. It's kind of weird because you wanted to accomplish that in one day, but it would be the same if it was 59 outside and we wanted it 60 in here, and we wanted to maintain that for 20 days. That would also be 20 heating degree days. And that's what that's why we're going through the trouble of figuring out like how much heat is in the house. Okay, so that's the volume. Now let's figure out the heat. So I used big Q for heat before. Now the bigger the house, the more heat you're going to need. So that's V. What else do we care about in terms of heat? What's another variable we might use? Heat loss. Yeah, and we'll get to that because ultimately, if you just shut your furnace off, you are going to lose all that heat. Insulation's going to matter too. Absolutely. We need to know the temperature of the air, and so I'm just going to.
Air distribution in the aspect.
Yeah, for air distribution, we're going to assume that everything inside that building is perfectly distributed. You know that okay. So yeah, it might be a little hotter near the ceiling, might be a little colder at the ground, but we're just measuring the average temperature in the room. We're just going to worry about one temperature for now. Okay, so we got the volume, we got the change in, and this is just one variable, change in temperature. And then there's this other thing just called the specific heat. So I'm just going to write this as C sub P. And Steve, I think you were mentioning that the elevation matters a little bit, and it does. But what we're going to do is just pluck out a single C sub P, a single heat coefficient for air, and see where we get. So this is our heat equation. In this case, there's not really any heat transfer occurring. You can think of this. It's not. Well, we'll get to enthalpy eventually. So let's go out and look up the. I always kind of like to dink around on. Oh, this is actually a pretty cool graphic. If you take a look here, this is just showing that something that is hot and left alone will eventually be cool. You know, coffee cup, wood stove, etc. And we will do heat transfer in a little bit, but let's do one more thing here. Heat capacity. Heat capacity is that little C sub P thing that I mentioned. Heat capacity, sometimes called thermal capacity. Let's just get right on down to it. Typically, there's a table. We'll skip all the differential equations and just get to the part that we. Yeah. Now, so air has a heat capacity, water has a heat capacity, lead, metal, etc. Man, these wiki pages get longer all the time. Okay, now the thing that we care about is are the units there. So joules, we already know is energy. Grams to the -1 just means that there's a mass in the denominator. And then Kelvin to the -1 means that you got temperature in the denominator too. That works out almost perfectly for us. This is the number I was after. It's not that exciting, it's just 1. At sea level, yeah. And Steve, I think you were alluding to the fact that it's going to change. And like I said, maybe a 2, maybe a 5% difference. And right there, you can see that, yeah, it's about.
The R value is going to make that.
It's just it's just a 1% difference. So it's kind of down in the weeds a little bit. So that's the number, and that just says that 1 gram of air, and if I'm not mistaken, I think a gram of air. So
0.01 grams of air.
yeah, a cubic meter of air weighs about a kilogram, and there's about 1,000 liters. Well, there are 1,000 liters in a cubic meter. So it just means that 1 liter, this one liter of air weighs about a gram. There's 29. If I had 29 of these full of air, I would have an ounce of air. That's why it took humans so long to figure out that, yeah, air has mass and all that, because it's not very heavy. Okay, so 1 joule per gram per Kelvin. Let's put that in our little computer here and see what happens. So remember, we've got our volume. That was 450 cubic meters. We've got our change in temperature. That was the 20 degrees. We'll just stick with that. We're going to have to convert it from Fahrenheit to Celsius. And now we have our specific heat capacity. We've got one equation. There were 4 unknowns. We just checked off 3 of them. So we got 1 equation and 1 unknown. Now we can solve our problem. We can figure out how much heat is in the house, and we can figure out how many dollars worth of heat that is too. Okay, now it's going to take a little bit of finagling, because right now I've got 1 joule per gram per Kelvin. So let me write that out. 1 joule per gram per Kelvin. That's my C sub P. Pretty simple. The volume, I'm going to have to change that just a little bit. And what I'm going to have to do is I'm going to have to change that to mass. So let's do it this way. Let's do it this way. I know that mass equals density times volume, right? No brainer there. So let's figure out what the density of air is, and then we can figure out how much mass, what the mass of the air is inside, and we can get down to business. Anybody remember the density of air? I think I just said it's about a kilogram per cubic meter. Let's see if I was right. 1.2. Okay. 1.225 kilograms per cubic meter. So let's just do that. So the mass equals 1.225 kilograms per cubic meter. My volume is 450 cubic meters. So the mass, let's just do that little bit of math. 450 times 1.225 equals 551. Let's make sure we got the units right. Yep, kilograms. 551. Here we go. 551 kilograms. Seems like a lot. I mean, there's a half ton of air in your house. Like at first it didn't seem like much, but there is. There's a half ton of air in your house. 550 kilograms. Okay. So I'll just write it right here. So I've converted that volume into mass, because I know that I'm dealing with grams and not cubic meters, because that's how the heat constant was given to me. So 551 kilograms. I am now going to need to do something like this, where I've got 1,000 grams divided by 1 kilogram. Let me see if I can grab that thing. Something happened with my little lasso. I used to be able to lasso the. Something happened. Okay. Well, I'm just gonna jam my delta T in here. I know if I said so 20 degrees Fahrenheit. I want to get that into Celsius. All I'm dealing with here is the change in temperature. So I know Celsius is just 5/9, so 20F, just go in here, 20 times 5 divided by 9 equals 11. So 20 Fahrenheit is 11 Celsius. 11 Celsius is the same as 11 Kelvin, which are the units of temperature we're working with. So 11 Kelvin. I'm going to raise my house temperature 11 Kelvin. So again, getting back before, all these problems are solving 3 problems at the same time. We've got our numbers. We've got a number 1, number 551, number 1,000, and number 11. We've got our powers of 10. We got a kilo kicking around there, a kilo kicking around there, nothing on the other ones, and then we've got our units. Well, let's go ahead and take care of our units right now. And I'm going to use a red pen for this. So I'm going to cross through the grams. I'm going to cross through the kilograms. I'm going to cross through the kelvins. I've taken care of all my units. At this point, all I need to do is run those numbers. So 1 times 551 times 1,000 times 11. Let's see what happens. Yeah. Times 551.
6,450,000.
Yeah, so 6.1 joules, or yeah, no, 6.1, or sorry, I'll just write it this way, equals 6 comma 1, what was the next number, 2, we'll just, and again, I'm just going to keep this to 3 significant digits. I mean, when are you ever going to measure something in something smaller than a 1/10 of an inch, whatever? So 3 significant digits is fine. This is joules. So now I've got 6.12 megajoules. Now, I now have to convert. So I'm still kind of a far way from converting this to money, which is what I want to do. What units should I take? Do you ever look at your power bill and say, oh, I bought this many megajoules of heat? Not so much. What do you usually pay in? Do you remember? For heat, if you're on natural gas? You're paying for CCF. You're paying for 100 cubic feet of gas. So let's see if we can't go from megajoules to CCF. Because that's typical, most houses are natural gas. So let's take that, see how many megajoules there are in a CCF. That might be standard, it might not. We might have to actually go through BTUs first, or we might have to go through therms first. Let's just check that out. And again, there's not one single way to do this. You should check your work and do a couple different ways. If you're online and want to follow along with me, I'm just going to kind of blindly say megajoules to CCF. See what happens. Kyle's converter, what do you have? Now, what I really want to do is Well, I know I've got 6.1. Let's see what happens. 6.12. Okay. 5.8. I've done this enough times, I know that's about right. And you also might say, well, gosh, how much is that? 6 cubic feet? Well, that's, about the, it's a few gallons, it's 1 foot by 2 feet by 3 feet, it's the size of a large suitcase. And you sort of off the top of your head, like, well, could that much natural gas heat my house 11 degrees Kelvin or 20 degrees Fahrenheit? Probably. So I'm gonna just for now, I no reason to doubt this, but I'm gonna say that's 5.8 cubic feet of natural gas. 5.8. I'm just gonna call it CF. Natural gas. Which is the same as 0.058, right? I moved the decimal place over, CCF, 100 cubic feet, C for 100, century, you got that. Let's just see what that is in dollars. You guys know what the cost of natural gas is right now? Natural gas. Weekly update. There's a few different ways to.
8 cents, 10
This is in. Okay, there's China's usage. And let's just type out CCF. And it's weird. You look at some of these tables, and it's different. Like residential is going to be different. Industrial is going to be something else. Okay, U.S. price of natural gas delivered to residential customers. This is in dollars per 1,000 cubic feet. Let's just say 10. Let's say it's $10 for 1,000 cubic feet. Do a little bit more math here. So let's just write it out this way. So $10 per, and I'm gonna use. There are a lot of different ways to write this, but I'm just going to write it like this: KCF. That is not standard, but I know that K is 1,000, and it's going to work for this purpose. If I run this again on the top, I can say this equals 0.0058 KCF. Those are my units. And now I can tell how many dollars worth of natural gas it took to heat my house. And when you're arguing with the kids about closing the door or not, you can say this: you're going to waste this much energy if that leaks out. So really now all we have to do is say 0.0058 KCF. So again, we've got a number in there, we've got a power of 10, we've got the unit, the CF are the units, times $10 per KCF. Equals 0.06 bucks. So, at any given point in time, if you got a 20-degree difference between the outdoors and indoors, you got 6 cents, you got a nickel's worth of heat in your house. There you go.
So that's what 8 cents is, right?
What's that?
You're saying 8 cents.
You said 8 cents before you started.
8 cents for what?
That's what the cost.
Oh, I think I asked before what the cost was. Well, anyway, was that your guess though? About 8 cents in the house? Oh, okay, yeah, so that's a pretty good guess. If it's a well, and we've just done this linearly. If you took that and added 30% to it, want it a little hotter, so yeah, it'd be more heat. Okay, now, down the road, when we do the blower door and all that, we'll basically say, you know, how quickly money is leaking out of the house because there you go, we just converted energy to dollars. All right, how are we doing on time? Yeah, well, I think that's a pretty good place to stop, and we'll come back and we'll do different types of heat transfer.
So if you figured out that you had a 30% heat loss, you would have to add 30% to that to make up for it? If you were losing that 30% while during that time you were heating it up at 20 degrees?
Yeah, what we'll see, and we might do a little bit of fluid transfer next week, what we're going to see is that you're always losing heat, either by convection, conduction, or radiation.
That's in a perfect world where you're not losing any heat while you're
Right,
heating it
right.
up.
But the fact is you're always, well, not always. I mean, most control systems, you get a little bit hotter than you want, and then you lose it, and then you get it hotter again. It's always a little bit of a roller coaster like that, but.